And so we have our last keynote of the day, Professor Eiman Kanjo. And Eiman is a professor of pervasive sensing at Nottingham Trent University, also provost visiting professor at Imperial College, and largely involved with this organization called tinyML. So Eiman is a computer scientist and an engineer and has been thinking about the problem of sensing. And so this could be sensing in the environment for levels of pollutants. It could be sensing in biology for disease. And tinyML is the idea that I alluded to earlier, that we would like to put some of these very advanced AI technologies on edge devices that are too small to have the full model on. For example, if you wanted to do compute on your phone or on some kind of sensor, it would need to be much smaller, and we'd like to preserve a subset of capabilities. And so we're going to hear a bit about that today in our last keynote. It's a real pleasure to have you with us. Thank you for coming down for the day. And when you're ready, take it away. Yeah.
How about this?
I think that's the right clicker, yeah.
Okay, thank you very much for inviting me to this great event. I work in the area of pervasive computing, which means the world is my lab. So we embed technology, small technology, anywhere, in a park, in a hospital, in a city, on a street, at home, wherever. And over the years, I've been working on many technological solutions. So I'm a technologist, a computer scientist, and engineer in some way. So we've been working with end-user organizations to solve real-world problems. For example, healthcarers. We work in the sector of defense, in agriculture, and so on. So today I will talk about tinyML, Edge AI, and its relevance to healthcare, especially in terms of wearable. Just before I start, can I ask how many people have wearable in here? How many of these are smart wearable? Can I ask the ones who don't have wearable, why don't you have wearable? That's what? Any reasons for not having wearable? Privacy? I could hear someone saying like they don't want to. Okay, charging power is a problem. Okay. Price, cost, data, right? Yeah. I don't have a wearable, by the way. I mean, I have wearable in my lab, many of them, but I don't use it because I like to protect my data. The other thing I would like to ask before I continue is how many people work with the large language models? Okay, like few. Okay, I'll try to change your mind about them if I can. So just imagine these large models that require so many computational resources, so many parameters, GPUs, MPUs, and TPUs these days. All these resources are expensive. Now imagine that we distribute AI. So everybody in here, everybody in the world, have access to AI. So we democratize it. And then we have a way where we reduce these large models into smaller models and embed them on small devices. And that's the appeal, is that you can use, to some extent, a small, tiny device that can run AI, again, to some extent, there are challenges, and can do things on the go. I don't know if you've seen this piece of news, but NHS said, I don't know when they will do this exactly, but they said they will share health record with patients on their apps, so it's easier to be accessed by their doctors or by the patients as well, which is great, which means there's a possibility that we could access our data on our personal devices. Just before I talk about tinyML, I want to say that you must have heard of Internet of Things, and many people get confused between Internet of Things and Edge AI. So Internet of Things is some kind of a sensor that you put somewhere and can sense and gather data and send it to the server somewhere. It could be to a nearby mobile phone, or it could be to the cloud. And that's an example. For example, this is an application where IoT has been used to monitor if someone is active in their house, to make sure that they, if they have some kind of a condition, they don't disappear for a long time, and their relatives can keep an eye on them. The other thing, I have the statistics, which I'm not too sure if it's quite accurate, but there are a lot of data coming from IoT devices. There are many IoT devices in here. But the question is, how much of this data do we really use? Probably very, very small portion of it. So we don't really analyze the data. And one reason for that is that this data has to be transferred to somewhere else to be analyzed. So we need to find a way where we could analyze it on the spot, where we need it, so we don't even miss part of the data in the transmission. Now, tinyML can bring all of these things together. And it's the same way, it's Edge AI, but it's a small edge device that has sensing capabilities. It has machine learning capabilities as well, some kind of processor or dual processor or more, or even TPUs in some cases. And then, obviously, these sensors can gather data, and then the data is processed directly by AI, and then there's an action or intervention on the go. I don't know how many people know what microcontroller is. Okay. So microcontroller is more or less a small device with a processor and input, output. You can plug things into it. You have it in the wearable, for example. And these microcontrollers are getting smarter every day, and they're getting cheaper. So that's the appeal of technology. It's low cost, low energy. There are some microcontrollers, which I will talk about very shortly, that can cost less than £1. So they are cheap. They can process data on the spot where they are needed without the need to transfer the data. But obviously, we have to make sure that the model is small and efficient, and that's one of the challenges, but it's possible in many ways. I work with an organization called tinyML Foundation, based in US, and they promote the concept of tinyML. We have various events and activities, including the tinyML Summit and the European event and so on. So you are welcome to look at the website, tinyml.org. Going back to the microcontroller, comparing a microcontroller to a workstation or a PC, you could see how much, the level of resources are, on microcontroller are very limited. So you have really very small memory that can handle the data. Small processor. It's getting better every time, but they are very restricted comparing to a PC or a workstation or some of these large data centers. And just to put things, to show you where the AI is processed on a microcontroller, you have here the RAM, and you have the flash, you have the weights of the network, for example, and the activation matrices. Just to give you a flavor of some of the microcontrollers, which I mentioned earlier. So there are many, like, for example, mobile phones. You pick up this mobile phone because this mobile phone is relevant, or it can give you this kind of capabilities. But when it comes to microcontrollers, you can pick up that device because you have a specific application. So for example, if you're looking at something cheap, reasonable, so there are the Arduino. This is one of the early microcontrollers, which appeared many years ago. And then, for example, we use this one, which has a long-range communication tool called LoRaWAN, if you are familiar with LoRaWAN, which is low power energy, similar to Bluetooth, but wider. So that's one of the microcontrollers we use for agriculture. And then this tiny ASP is very, very cheap. We used it during contact tracing to communicate between different users. I have like hundreds of these in my lab. And then some of the recent ones, Portenta, for example, it has dual processor. And the memory started to get bigger and bigger. And now we have the Coral Edge TPU, for example, by Google and Arduino. And this one has dual processor and TPU and a bigger memory, which means what we have been doing over the past few years, trying to crush the model, make it much, much smaller. Now we can breathe a little bit and talk about the reasonable models. But these models still have to be smaller. We're talking here about 1, 2 megabyte models comparing to a very big models. Just to give you an idea about microcontrollers and where they are used, and you could see still we are, we're not making use of them for healthcare. And you could see the healthcare sector comparing to other sectors, and how many of these microcontrollers are in the market. So there are a lot of microcontrollers sold, but we're not making use of them, which is a waste. If you are wondering how does tinyML work, so as I said, you have this device, you have a sensor, but the interesting thing is that you could have a wearable without data. You don't produce data. That makes sense. You don't need to worry about the concept of sharing data because there's no data. You get the data from the sensor, right? And then you process it, and then you throw it away. So I could like point my camera at you and then process the data and say there are, I don't know, 100, 200 people in here, and the output is 200 people. But the actual images, the frame themselves, are not stored, not shared with anyone. And that gives you some peace of mind that there are no data. So I shouldn't worry about it, even if the sensor itself seems to be intrusive, but actually there are no data. So there are many things that we do in order to enable or to make device, or we call the device a tinyML. So it depends again on the application. You have a sensing device, you have to do the data labeling and collection, you have to do data processing, quantization. I'll talk about this very briefly. Optimization. A lot of optimization happens because you want to have reasonably active, efficient, model, accurate enough, but also small enough to fit on that device. You could use federated learning, for example, if you want to distribute the learning between different devices, tools, and we do this a lot for our farming applications. You could use other techniques in order, for example, personalization on device learning and so on. So these are just some of the building blocks of tinyML. And of course, the idea is that we increase the sparsity of the model, because the more we condense this model, we reduce it, we compress it, we make it smaller, the better, so it can fit. We want to make it fit into very, very small storage. And what happens, for example, if you have a wearable or a device that has multiple sensors? These are some of the issues that we have to deal with, especially for, let's say, medical wearables. If you have multiple sensors and you give this device to a patient, and then at some point, all these sensors are switched on, the battery will run out in no time. So we look at, for example, techniques on how can we manage these sensors? How can we keep some of them on and off in order to not consume too much power? This is one of the projects that we worked on in terms of managing the sensor feed in a way that there is a model that can sense context. And depending on the context, some of the sensors will be switched on and off in a way that we could preserve the power on the device. The other problem that you'll find when it comes to healthcare is that you will give the device to a patient or a user, and this device has to be personal. So it has to deal with personal data, my own data. So we need to find a way for this particular user to collect their own data, so we fine-tune the model which means we have to label the data on the go. How can we do this? That's another challenge that many researchers look at, because everybody's interested in optimization, the next model, and so on. But this is a very practical problem. Like if you want to collect data on a particular device, you need a labeling technique. Again, we've done research. We have a paper in this area called Label Sense, where we put actual physical buttons on the device to enable the users to collect the data and label it on the go for a short period of time, like for over a few days, until the data can be personalized. This is a fidgeting cube, by the way. I mean, I don't know if you know what fidgeting cube is. A small device that you could buy on Amazon for £3-4. They say it can tackle stress. So we put some microcontrollers inside and try to see if we can sense well-being and enable the device to react to that. So personalization, so this is the prototype that we use to add on-device labeling technique. So personalization is a very big problem that needs to be solved. We try to solve it, and we use on-device learning, which means when you have the device, say that you bought this device, we need to personalize it for this particular user, and then we have to fine-tune or retrain the model on the device. And that's why having a microcontroller that is able to retrain the model with the user's data is very important. Again, this is an area of continuous research because, subject to the capabilities of the current microcontrollers and software available for it. I will go very quickly through some of the techniques. I mean, there are many, many details here, but I'm not going to cover all of them. If you are, for example, trying to take a big language model or any other model and you want to compress it or reduce the size of the model to work on a microcontroller, you have to first look at, as I said, increasing the sparsity of that model, which means pruning is one of the ideas. You know how you prune your tree at this time of the year, you prune your model. So you cut some of the useless neurons in the model. You try to keep the ones that are contributing to the learning. And there are many techniques for pruning, and you could also have structured and unstructured until you have only the parts of the model that matters. Also, quantization is very important. Techniques is used in many areas other than machine learning. For example, if you have a continuous set or range and you want to map it to discrete range, so you use quantization. And it's very important in the way that, for example, you have 64 floating point numbers and you want to condense it or make it smaller to 32-bit or 8 bits or even 1 bit. You could have binarized neural network. And that's an extreme case. So you really have this very, very small model, but that can help in some cases. And there are many techniques where you could rescale the range, for example. Another widely used technique called knowledge distillation. And the idea here is that you have a very large model, a teacher model that is trained separately, and then what is called soft labels out of that model is used to train another student model. So you use a teacher model, student model that can learn from the previously trained model, which can improve the accuracy of the student model. Another technique you might have heard of is called neural architecture search, which basically is using AI to design an AI model. In a way, you tell AI, I want this model to be efficient. You give some parameters, you give some restrictions, or you have the search space, which you choose, and then you should get some kind of efficient model at the end of it. Now, going back to healthcare or health and well-being in general, as I said, you could do inference on the device. And you could see here some examples of our previous works. I mean, we tend to build our own wearables. And very often when we deal with these wearables, we deal with two types of data collection patterns, passive data collection or dynamic. Like for example, if you have again well-being device or health device, you could get continuous data from that device passively while you are sitting here. I'm saying like, okay, I'm moving, I'm standing, or you could ask the user to add some input. Like for example, you could ask them for self-report to say like they are happy or not happy or they doing well. You know, you could have subjective data added to that or different categories. Also, very often when we do this kind of research, we have to work with users. So there's the concept of co-design, co-creation. So very often we bring the users to our lab. They do 3D printing, prototyping. They tell us what kind of device, how they want this device to look like. This is very important. It's difficult when you have a group of engineers, computer scientists trying to design and solve a problem without the involvement of users. So we do this very often. And then in terms of like where do we use these devices once we have designed it, co-designed it, or co-developed this device? We work on a wide range of applications related to well-being, like for example, as I said, the fidgeting tools to tackle stress, anxiety, for example. We've done a lot of research on linking pollution to health conditions, for example, using quantitative, objective measures, having a device that can analyze the data on the go in urban area, for example. I'll talk very briefly here about one project that we have set up in north of Nottingham, near Sherwood Forest. It's called Tag With Me, and the idea of this platform is to motivate people to be physically active. So we use the combination of wearable devices, mobile phones. I teach mobile development, by the way. So I have very good experience on how to develop a good mobile app. And then we used IoT devices, tags, as you can see here. And the whole idea is that you have a community that is living in a particular area, and you want them to go to this green space, walk more often, socialize, and, but without making it hard, make it accessible for them. So that's the idea of this platform, and I've been told at some point this is something called social prescribing. I don't know how many people know the concept of social prescribing, but it's like some kind of non-clinical intervention for people with long-term conditions or people who are struggling somewhere or another related to their healthcare. So we deployed this in Nottingham Park. And at some point, you could see here the path that the users take around the park. And that's one of the tags that the users have to go and tap into in order to say, I reached this particular point of interest. And then if they reach like 10 points of interest, they get some rewards from the park. And you could see here, there are like, for this particular app of this particular park, there are like 15 places they have to visit. Once we've done this one, we have had a request from a local hospital, mental health hospital in Nottingham. They asked that we deploy similar kind of platform in their hospital. And the reason for that is that they said their patients have to walk around the hospital on daily basis, but the path that they have to walk through is very boring. So we came with some ideas of how can we make this more interesting. We held some workshops with patients to create their own paper maches or their own sculptures, which was very interesting. And then they managed to put it around the hospital. And you could see here the AI algorithms detecting these sculptures on the go, part of the experience. So, as I said, this platform has been used by hospital. I get many requests on daily basis or like weekly basis. Is that many other parks, many other places, they want to look at the idea of how can we use technology to promote health and well-being. And that's the path that the users or the patients take. That. So there's a huge potential for technology. I mean, I could go on and talk about many applications. I know I have limited time here, but if you are interested in the concept of tinyML for healthcare, for example, I'm happy to talk about it in more details, because I feel like the technology is there, but we're still not making use of it. So it's really the right time now to start to think of how can we utilize these microcontrollers or devices that are already available that are powerful to some extent to be used for self-management, for personalization, for devices that can process the data on the go while protecting privacy, while keeping the device low cost, low energy, which can democratize AI for all. Thank you.
Thank you very much for the great talk. We can take a question from the audience if anyone has one. Okay, so because we're a little bit pressed for time, if no questions, we'll thank Eiman again. Thank you very much.